Oh, you absolute legends. When predicting the solubility of an organic compound, two things to consider are, is the hydrogen bonding present and the molecular weight of the organic compound. Now, because we're talking about organic compounds, the number of carbons is a way to think about the molecular weight here. Now, considering alcohols, alcohols can hydrogen bond with water molecules. Let's show that hydrogen bonding with some models. Here is a molecular model kit of propanol. The prop means that it has 3 carbons, and the ol at the end, OL, means that it's an alcohol. It is a primary alcohol here. It has the alcohol group here, the oxygen, the O and the H. And these 2 bunny ears right here, these are meant to represent the lone pairs of electrons on the oxygen atom. So oxygen has its octet, 1, 2, 3, 4, 5, 6, 7, 8. I didn't show all the hydrogen atoms here just for clarity. This is a water molecule, H2O. We have the oxygen in the middle, 2 hydrogens on the outside here. Now it also has bunny ears to fill out oxygen's octet that's in there. So this oxygen has its octet. Now hydrogen bonding looks something like this, where we have the alcohol, OH, and we have the water, oxygen, lone pair, and we have this negative lone pair of electrons attracted to the positive nucleus of this hydrogen atom here. Note that hydrogen, hydrogen only has 2 electrons around it, and both of those electrons are in a bond here. So you have a naked nucleus or a de-shielded nucleus. Now, when a nucleus is de-shielded, its positive charge is exposed. All nuclei everywhere in the universe are positively charged because they're full of protons and neutrons. So this is a positive-negative attraction here. Here is another hydrogen bond between the hydrogen of water and the electron pair of the alcohol. This hydrogen bonding means that the water molecules are going to join in a party and create a solvent sphere around this propanol molecule here. So this is meant to be models showing how the hydrogen bonding interaction occurs. Now I mentioned molecular weight, the number of carbons. For every 1 alcohol group and 3 carbons, that's the ratio that you can predict something would dissolve in there. So for example, here we have 1, 2, 3, 4, 5, 6. 6 carbons, and it's a primary alcohol, hexanol. Hexanol, I would not predict is soluble in water because its molecular weight is too high with respect to the alcohol groups. It has too many carbons with too few hydrogen bonding opportunities. It's out of ratio. Now, a ratio is about 1 to 3. For every 1 alcohol group, 3 carbons, it should dissolve. So, for example, here, let me move these water molecules out of the way. Here is a diol. The diol, because it has 2 alcohol groups, it has 6 carbons and 2 alcohol groups. I would predict this to be soluble in water because it fits this 1 to 3 ratio of hydrogen bonding places or alcohols to number of carbons. Consider the sugar. Let's build it up here. This explains why sugar is so soluble in water. Sugar has 6 carbons associated with it. And I'm just going to try to build a quick random sugar molecule. I'm not by any means saying that this is representative of sugar. Do I have enough to make it? But sugar, C6 H12O6 is 6 carbons and 6, 1, 2, 3, 4, 5, and then 6. Sugar is an organic molecule that is very soluble in water because it has so many hydrogen alcohol groups. Throw this carbon here. Now, I'm not saying that this is an actual sugar molecule. I wouldn't be surprised if it is, but I have no idea how to name it. It reminds me of a crab as soon as I put this thing together here. But we have 6 carbons present in a 5-carbon ring with 1 poking out here. So that's our 6 carbons. And each of those carbons has an alcohol group pointing off of it. So it is a 1-to-1 ratio of hydrogen bonding places to molecular weight, or number of carbons. This is why sugar is so very soluble in water. So when predicting the solubility of alcohols, consider the number of alcohol groups with respect to the number of carbons that are present. Thank you.